We've just talked about the look for a pattern strategy of problem solving. We'll now try to apply it to a particular problem that you might come across in real life. As always, we'll employ Polya's problem solving process: understand, strategize, solve, and look back. Here's your task. You're given data for 1,000 students at a liberal arts college who are surveyed about their career prospects after graduation. The college provides you with the following data. Information is given for students from 4 majors: humanities, social sciences, science, and engineering, and the arts. The number of students in each of these 4 categories is also given, as well as the mean salary for each category and the standard deviation on that mean. You're also told that the college interviewed 10 of the recent graduates and found that all 10 were dissatisfied with their post-graduation incomes. Historically, you're told, research shows that students earning above the mean income are happy with their incomes, while students earning below the mean income are unhappy with their incomes. You're approached by the dean of the engineering school, who recently read these survey results. His goal is to have 99% of all engineering students be satisfied with their starting salaries, and he wants to know whether he needs to devote additional resources to career services to accomplish his task. Now let's apply Polya's problem-solving process to this question. Based on what the engineering dean has told you, your objective is to determine whether 99% of engineering students are satisfied with their starting salaries. Let's look at the information you have to accomplish this objective. You know the number of students in each of the 4 majors and the mean salaries for those students, so it's possible for you to calculate the overall mean salary. You also know the standard deviation of the salary for each of the groups of students, so you could use the empirical rule to compare the engineering population to the overall mean. Finally, you know that the mean income students with mean incomes above the average are happy, while students earning below the mean income are unhappy with their income. Are you beginning to formulate a strategy? Let's think about how we can solve this problem. We want to look for a pattern. That is, we want to look for the pattern of mean incomes in engineering students compared to the pattern of mean incomes or income distributions of the overall student population and compare those 2 distributions. We can do this by calculating the overall mean for the graduating student population, then comparing this mean to the engineering population by leveraging the empirical rule and standard deviation data we were provided. We know that the goal is 99% happiness, and that if a salary is greater than the mean, this will lead to happiness. So we can use the empirical rule to answer the question of whether 99% of the student engineer population is greater than the mean. If the engineer population is greater than the mean at a 99% level, then 99% will be happy. Now we go ahead and implement this strategy to solve the problem. Let's first calculate the mean salary of all students at the university, because this is the value that we want to compare the engineering population to. We know that the mean is equal to the sum of all the values divided by the number of values. We can calculate the sum of all the values by multiplying the mean for each population by the number of students in that population. This has been written out below, and if you'd like, you can pause the video and practice using a calculator to calculate this number. You should obtain a value of $43,800,000 earned across all majors. The number of values is simply the number of students. We were told up front that this was 1,000, and we can also calculate this by adding the number of students in each major from the table. So the mean is just the sum of all the salary earned divided by the number of students, or $43,800 on average per student. We've now calculated the mean for the overall graduating student population, and we want to compare the engineering student distribution to this mean. We know from the empirical rule that 68% of a population will be within plus or minus 1 standard deviation of the mean for that population, 95% will be within 2 standard deviations, and 99% will be within 3 standard deviations. The science and engineering mean is $60,000 for starting salary. We want to know whether 99% are above the mean for the overall mean. So we subtract 3 standard deviations, which accounts for approximately 99% of the population, from the engineering school mean to calculate the value below which only 0.5% of students fall. Calculating this value gives $60,000 minus 3 times $2,000, the engineering standard deviation, is $54,000. So 99.5% of science and engineering students fall above this value. Now let's assess the implications of this information. Recall that the overall mean for all students was $43,800, the science and engineering mean was $60,000, and 99.5% of engineers make more than $54,000. So 99.5% of engineers are happy because happiness is simply a result of salary being greater than the mean. Thus, the dean has met his goal of having at least 99% of students be happy, or at least according to the normal curve that's defined by the empirical rule. Our last step in the problem-solving process is to look back. Now, we've answered the question that we were asked. We can anticipate that the dean might ask us about that other data point we were given. That is, recall that 10 students were interviewed about their career prospects and their starting salaries, and all 10 were dissatisfied. The engineering dean might want to know what the probability of this occurring is if indeed 99% of engineering students are happy. After all, 20% of the student population was accounted for by science and engineering students. Is it really likely that no or very few science and engineering students were interviewed? Well, the good news is that we can calculate this. Let's take a quick look back at our table. If we were to apply the empirical rule again, we could determine the proportion of students of other majors who are dissatisfied with their salaries, calculate the overall proportion of the population that's dissatisfied with salary, and then use that information to calculate the probability that 10 dissatisfied students would be picked. Now we can see that for humanities majors, the mean salary is $40,000 and the standard deviation is $1,000. We know that almost all students will fall within 3 standard deviations of the mean, and the upper bound on this is $43,000. So that means almost all students are below the overall mean if they're humanities majors. A similar thing is true for arts majors, whose mean salary is $32,000 with a standard deviation of $1,000. Looking at social science students too, we see that the mean is $42,000 and the standard deviation is $1,000, which means that approximately 97.5% of social sciences students have a salary below the mean, because the mean is approximately of the overall population is approximately 2 standard deviations above the social sciences mean. So we can approximate and say that for the most part, humanities, social sciences, and arts students are dissatisfied with their salaries. Because these students account for 80% of the student population, the probability of being dissatisfied with salary is approximately 80%. So that to answer the engineering school dean's probable question, we'd want to calculate the probability of picking 10 such students. Recall that when an event is the combination of a bunch of discrete events, then the probability of that greater event is the product of the probabilities of the individual events. The probability of picking a dissatisfied student is 80%, so we simply raise 80% to the 10th power, that is, multiply it by itself 10 times, and come out with 11%. This means that the likelihood of pulling only non-engineering or non-science students from the population is about 11%. It's not a huge probability, but it's also not outside the realm of realistic probability. So we can tell the engineering school dean it's not all that unlikely that simply no engineering or science students were interviewed, and that's why there were no students who were satisfied with their salary in the population.